Hello, Mr. Ingram here. Welcome to today's lesson on logistic growth and applications. Today we'll explore how growth that initially looks exponential eventually slows down due to real-world limitations, and we'll model this using differential equations. Now, in natural growth, the rate of change is proportional to the population present. And this is modeled by the following differential equation. But when there are limits or limitations, such as food, space, or other resources, we use a different model. I will talk about that in a moment. Now, we see the law of natural growth and decay is a separable differential equation, and we just want to recall solving differential equations in general. It's good practice. And we see that our solution is y equals a times e to the kt, where a is an arbitrary constant. Now, this model that we're using today, right, is called logistic growth. So we want to talk about when this is appropriate. Logistic growth happens when an environment can't sustain unlimited growth. As the population gets larger and resources get scarce, causing the growth rate to slow down and eventually level off at what we call the carrying capacity, notated by K. So our population P and our carrying capacity K. Now, the logistic differential equation is as follows below, right? It's dB dt equals R times P times 1 minus P over K, all of that in parentheses, where R is the growth rate and K is the carrying capacity. Now, we won't actually go through the process of solving, but our general solution is P of t equals K over 1 plus B times e to the negative RT, where B depends on the initial condition. So some important things to note here. K, the carrying capacity, R, the growth rate, and B depends on our initial condition. Now, solving a logistic growth problem, we kind of have if you can think of it in a 4-step process. You set up the logistic model, solve for B using the initial condition, solve for R using a given data point, and then write the full model and predict future values. So we can kind of break the problem up into multiple steps and approach it that way with that type of flow. Now, in example 1, we're going to start off by modeling the growth of an elephant population. A conservation project introduces 50 elephants into a new wildlife reserve. The reserve has a carrying capacity of 400 elephants. After 3 years, the population has grown to 120 elephants. We will find the logistic model and predict the number of elephants after 10 years. So we're going to first start with setting up the logistic model. Let's go ahead and write our general equation down. P of t equals K over 1 plus B times e to the negative RT, where K represents 400 elephants. Our initial condition our initial population was 50 elephants, right? Our time initially we could say is 0 as well. So plugging that all in, we get 50 is equal to 400 over 1 plus b times e to the negative r times 0. Well, this will become 1, and so thus we're left with 50 is equal to 400 over 1 plus b. And thus, we can find our solution for b. 50 is equal to 400 over 1 plus b. It's just simple algebra at that point. We get 1 plus b times 50 equals 400. 50 plus 50b equals 400. 50b equals 350. B is equal to 7. And thus, we have found our value for B. Now, we're going to use the given data that we have to find R. We know that after 3 years, our population is 120. So P of 3 equals 120. We say 120 equals 400 over 1 plus, now we substitute B, 7 times e to the negative r times 3. All right? And we can simplify this or clean this up in a different way. We could just rewrite it so that it's a little bit cleaner. All right? Now from here, how do we solve? Well, we get 120 times 1 plus 7 e to the r equals 400. 120 plus 840 e to the negative 3r is equal to 400. And we just solve. 840 e to the negative 3r is equal to 280. I'm subtracting 120 from both sides. E to the negative 3r is equal to 1/3. Let's move this up just a little bit, or make it smaller. From that, we get negative 3r is equal to ln of 1/3, and r is equal to ln of 1/3 over negative 3. Our r value is approximately 0.366. Of course, we would find that value using a calculator. So now I can write my model. P of t is equal to 400 over 1 plus 7 times e to the negative 0.366 t. And because I have my model, I can now predict the population after 10 years by just plugging in 10. And I approximately get 339 elephants. So we see the process is pretty simple and straightforward. We're going to do another example, not dealing with animals. Now, let's say we can even look at the spread of rumors at a baseball camp. There are 800 participants at this camp, and 10 campers start the rumor. After one day, 25 campers have heard the rumor. We'll build the logistic model and predict how many campers know the rumor after 5 days. So again, step one, I want to write my logistic model. P of T is equal to K over 1 plus B times E to the negative RT. Let's identify what we know, okay? So we know that our carrying capacity, right, is 800 participants. We know that our initial condition, right, is 10. Okay? Now, plugging that in, we get 10 is equal to 800 over 1 plus B times E to the negative R times 0. That goes to 1. And again, we have 10 is equal to 800 over 1 plus B. So we then get 10 times 1 plus B is equal to 800. 10 plus 10B is equal to 800. 10B equals 790. B equals 79. So we have our B value. Next, we already did that in one step. So again, we kind of set up our logistic model, and we did it all in one step. So we can actually skip that example 2 slide. We're going to use this given data to find R. All right, so we're going to use what given data we have. All right, so after one day, 25 campers heard the rumor. Right, so after one day, 25 campers heard the rumor. So P of 1 is equal to 25. We have that data point. We also know that based on our model, P of T right now is equal to 800 over 1 plus 79 E to the negative RT. All right, and so we're just going to plug in, right? P of T at 1 is equal to 25, so 800 over 1 plus 79 times E to the negative R times 1. We can simplify that. Let's move that over. Let's make this smaller and move this over. So 25 is equal to 800 plus 1 plus 79 E to the negative R. Sometimes I just like to simplify things. It's just a good intermediate step so you don't make mistakes. I'm going to multiply this all by 25. Right? I'm going to multiply on both sides by 1 plus 79E to the negative R. Okay? Then just going to solve algebraically. Okay, going to make more space. e to the negative r is equal to 775 over 1975, okay? And we can solve for this. We get negative r is equal to ln of this value. All right, so negative ln 5. And we're just going to put it in the calculator and approximate it. We get r is approximately 0.936. We have now found our value for r, and now we can predict, right, the number of campers that would have heard the rumor after 5 days, right? So after 1 day, we know it's 25. And so P of T is equal to 800 over 1 plus 79E to the negative 0.936 T. And we can plug in 5 to predict the number of campers that will have heard the rumor after 5 days. So we just simply plug in 1 plus 79 e to the negative 0.936 times 5. And you're just going to put that in your calculator. This approximately gives us 461 campers. So the biggest takeaways and ideas is that logistic models describe situations where growth rapidly starts to slow as resources become limited. The solving process is the same whether modeling population, rumors, or spread of disease. Okay. In your homework, you'll be introduced to a cheetah population and tracking squirrel populations in forest environments. You'll explore some models like this that we've done for practice. And so go forth and be great. Rewatch the video if you need any help, or please feel free to talk to your teachers or fellow classmates as we are working through the problems. Have a great day.